Hi everyone, my name is Pentapati. In this video, I'll be presenting a summary of my work on machine learning based wire RC predictions for monolithic 3D ICs. State-of-the-art flows for monolithic 3D ICs use a 2D type footprint that is compatible with commercial tools to optimize the 3D IC. Specifically, the 3D transformation of the 2D type designs requires additional legalization and routing stages, and this leads to a RC discrepancy between the 2D and 3D stages. So we analyze some of the net metrics versus the RC discrepancy to study how different nets behave when transformed from 2D to 3D and how different metrics can impact this discrepancy. So we implement a machine learning model that can predict these RC values of a net in 3D design just from their 2D metrics, and this training model also helps us to analyze the importance of various features towards this RC prediction task. And finally, we show the impact of PPA and RCs with the help of our ML model on some of the unseen netlists that we never used during training. So looking at different features, this is the feature importance of the model. So in the model, we use a total of 23 different features for the XGBoost regression model, and of these 23, 8 of them are net specific features to get various properties of the net, and 8 other are implementation specific, and these are used so that the model can be generalized for different net lists. So this can differentiate between two different net lists, and so the model can have slightly different estimations for like different types of net lists. And 7 other features are derived features that are derived from the previous 16 features, like a linear combination of 2 features, or a multiplication or a division of 2 features that we think would be interesting. And by training our model, we see like most of the features, only like 5 or 6 features are the most important, and most of these are net specific features, as we expect, because the implementation specific features are only useful in a very few cases where we have to differentiate the net lists. And looking at the RC histograms that result from the different models. So here we have like RC histograms for 3 different kinds of RC models. So one of them is the true 3D RCs. The orange one is the RCs from a pseudo 3D flow. Here the pseudo 3D flow we use is a compact 3D flow, and the blue one are the RCs that come from our model prediction. And we see that the orange bin is always like the orange bin has a lot of small values, which shows that the pseudo 3D is very optimistic in the RC estimation. So it estimates a lot of small RC values and doesn't estimate a large RC values properly. On contrast, we see that our ML model RCs do have a much better prediction, much better prediction of the capacitance as well as the resistance of the model. When we look at the results, we see that on the unseen netlists, the ML modeled RCs lead to almost greater than 30% reduction in the capacitance, root mean square error of the capacitance for the overall netlist, and more than 55% reduction in the root mean square error of the resistance, and up to 6% reduction of TNS is also observed due to the better RC predictions. And we see that even when the total net slack is reduced by up to 6 times, the total power is not changed by a lot, and this is because the optimization is done properly, and it's not just it's not just simply upsizing all the cells to have a better TNS. So it's properly upsizing at the proper cells and downsizing at the proper cells, so that the overall power is actually not increasing. And we also see that even though the total net slack is increased, has up to 6x reduction, the worst net slack is much harder to control, and we sometimes see an increase in the worst net slack because it only depends on very few critical nets, and we have to properly target these critical nets to control the worst net slack, and this requires further study. Thanks for your time. Please refer to the in-depth presentation or the paper for further details. I'll be glad to take your questions during the conference or via my email. Thank you.